The chaining mechanism also serves a chronological function. A block is successfully mined and confirmed every 10 minutes. This time-stamping process helps the network and users easily keep track of the millions of decentralized transactions. This also helps prevent double spending because the same transaction can't be mined or confirmed twice. If there are two transactions with the same unspent outputs in the memory pool, only one can be mined and the other will be simultaneously deleted. In my nonce explanation a few slides ago, I used a simplified lottery example using simple multiplication and two numbers. The Bitcoin mining process is a similar lottery system, but a lot more complicated. The entire mining process has very deliberate rules and processes. You can't just add any and every candidate block to the network. In order to be the miner that adds the next block approximately every 10 minutes, you have to win a competition to find a correct hash that solves a difficult math problem. The math problem stipulates that the first miner to produce a block header hash with a certain amount of leading zeros will be the winner of that block and be able to add it to the network. The target amount of leading zeros is related to what is known as mining difficulty. The more zeros needed, the more difficult it is to mine a block, and the more computations needed to arrive at the target hash. At the time of creating this, the target difficulty is 19 leading zeros, meaning the block header hash that is a result of combining the Merkle root, nonce, and previous header hash must begin with 19 zeros. Remember, with hashing, there's no rhyme or reason for why the input produces the specific output. So there's no set way to know how to produce a hash that starts with 19 zeros. And since the target hash is so specific, it makes it very difficult to land on such a specific output, meaning a miner's mining equipment must constantly change the nonce figure one number at a time until it finally lands on a header hash with 19 zeros. So think about it. Let's say you know what the previous block header hash is and you have your Merkle root, and then you use the number 1 as your nonce. And let's say that hash produces a hash that doesn't start with any zeros. So clearly you know that can't be the correct nonce. So let's say you change the nonce to 2 and it produces another hash that doesn't lead with any zeros. And let's say you continue to do this all the way up to 1,000. And with a nonce figure of 1,000, let's say you only have a block header hash with 2 leading zeros and then it FC8 something else, right? That can't be right. So the point is the nonce figure is constantly changed in a trial and error process until a miner luckily lands on a block header hash with the correct target hash leading amount of zeros. So I hope you can begin to conceptualize how difficult the mining process is. It requires a lot of computations. It requires a lot of nonce figures. It requires a lot of trial and error for a miner's mining equipment to luckily land on the correct header hash. When you hear of people saying how much electricity Bitcoin uses, it's because of this. It's because of the difficulty with mining. It's because there's no easy way to land on the correct header hash. It's because your mining equipment has to use a lot of electricity to run through so many trial and error computations to finally land on that correct header hash. And there are thousands of miners all competing for the same block every 10 minutes. Therefore, thousands of miners have machines running electricity, using a lot of electricity to do these computations. So this is an example of a 256-bit hash. And this is an example of a 256-bit hash with 19 zeros leading it. This number can start with any number, 0 through 9, or letter A through F. 16 possibilities per character. So finding a hash that starts with 19 plus consecutive zeros would take a lot of work. A miner that can produce such a block header hash has satisfied the proof of work requirement. I tell people to think of Bitcoin's proof of work like a puzzle. If somebody shows you a completed 5,000 piece puzzle, you can quickly determine that he or she put in the necessary work to complete that puzzle. You don't need to watch a video of him or her doing it. You don't need to sit there and make sure that he or she did it right. You don't need to get a second opinion to see if it's right. You don't have to wonder if the work can be trusted because you can easily see the completed puzzle and easily know that the work has been completed. This is the exact same concept of a miner presenting a block with the correct block header hash to the other miners. All miners are competing against each other for every single block. So as soon as one miner unlocks a block by using the correct nonce figure to produce the correct target header hash, the miner presents that header hash to the network, which signals to the other miners that the winning miner performed the necessary computations to crack the problem, i.e., an easily identifiable proof of work. It also signals to the miners to confirm that block to the blockchain and that the 10-minute lottery competition has been won and the next one is now starting. Like we previously went over, the last block's header hash is the starting point for the computations to find the correct hash for the next block. Let's now look at an actual block so that you can see all of these concepts in action with the actual blockchain. This is a screenshot taken directly from the public Bitcoin Blockchain Explorer on blockchain.com. This is the full block header, including important elements like timestamp, block height or count, meaning this is the 679,750th block ever to be confirmed, plus the number of transactions, the miner that won the block, etc. But we are going to focus on the three items in red, the three primary elements of a block header that we've already discussed: block header hash, the Merkle root hash, and the nonce figure. As discussed, the current difficulty is set to a target block hash of 19 leading zeros. The 256-bit hash shown here checks out with the requirement and begins with 19 zeros. Next is the Merkle root hash, which, as we previously discussed, is the master hash of all the transactions in the block. In this case, there were about 1,900 transactions, so this Merkle root is the digital blueprint of all of those transactions. Lastly, the nonce figure, the random number that the miner's hardware machine used to land on the correct block header hash. So that covers three of the four key elements. But what about the previous block header hash? Well, that's easy. All we have to do to get that is go back to the Blockchain Explorer and retrieve the block header hash of the previous block. Since we are currently on block 679,750, we need to check out block 679,749 for the info that we need. Upon clicking on that block, we are taken to the exact same block header screen that we saw with block 679,750. For our purposes with our current block, all we need is the block hash of the previous block. Again, as you see, that one started with 19 zeros too. So now that we have the previous block header hash, we have all of the four primary elements that went into the block header of Bitcoin block 679 and 750. We now have the previous block header hash, the blue star. We have the nonce figure, the yellow star. The Merkle root hash, the green star. And we have the block header hash, the red star.